Guys, very good morning. Okay, are you able to see my screen? PPT?
Um, no, sir.
I already shared, no? Already I have.
No, sir.
No, sir. Now it is not visible.
Okay, again I do it.
Now it is. Again, it is gone, sir.
Yeah, I don't know. That's what I'm worrying. Why it's this problem? Okay, now. Now are you able to see my PPT?
Yes, sir. Now it's visible.
Okay, guys. Okay, guys. Very good morning. So, okay, the last class we discussed, we started coupling, right? The concept, basic principle we discussed. So today, just we recap 1 or 2 minutes, whatever we discussed about coupling. Then we are going to discuss different types of coupling briefly, and each coupling we are going to discuss later in detailed manner how to design. Then concept, the derivations we are going to discuss. Those derivations will helping us to design our coupling dimensions. That's what our plan here. Okay, I mean, what is the coupling? Coupling is a mechanical device, right? I mean, the coupling is a mechanical device that can be used to join two shafts permanently. I mean, permanently in that sense here, not like welding as compared to clutch. It can be dismantled, it can be assembled. Okay, so we are going to use different type. We are using different types of coupling. I mean, for joining the input shaft to output shaft. I mean, the coupling also we are using the keys. With help of the key, with help of the bolt and nut, the coupling is securely connected on the shaft, input and output shaft, for power transmitting the power from input to shaft to output shaft through key, then key through key and coupling and output shaft. The power transmission order from input to shaft first. Yeah, this is the basics. From the power transmission from input shaft to key, key to coupling, then coupling to the again, I mean coupling to output shaft through keys. Okay, that is the order of power transmission in the coupling. Okay, now I mean, that's what, for example, a coupling is used to join the output and output shaft, whatever I discussed earlier here. The coupling is joined to output sort of the engine to input sort of the input shaft of the hydraulic pump for rising the water from the well. That is one example we I mean, that is one example. It's not limited examples. There are many applications. Okay, and based on the connection based on the input output shaft orientation, we can differentiate the couplings. See here, I mean, so the shaft to be used to I mean, the shaft to be connected here, the shaft to be connected by coupling, maybe a collinear axis or lateral misalignment or axial misalignment or maybe angular misalignment. Okay, angular misalignment. For example, these are the, I mean, this collinear axis. We can go for this type of muff coupling. I mean, sleeve and muff coupling. This is This is a sleeve and muff coupling. What is sleeve and muff coupling? We are going to discuss later. But when we are going to have, I mean, the couplings are in axial misalignment. Axial misalignment, we can go for all them coupling. I mean, two shafts are parallel, but the axes are offsetted. Just I draw this two shaft. This shaft is shaft one axis. Another shaft is parallel to the shaft to one. Another shaft is parallel to the shaft to one, but the axis of the shaft is offsetted. Right? Then this type of things, this type of power transmission from this is input shaft, this is output shaft, then power transmission can be done with the help of the Oldham coupling because two shafts are parallel but offsetted with respect to their axis. This type of places for the power transmission we can use the Oldham coupling. And angular misalignment. Angular misalignment. Already I told you that. I mean, Hooke's coupling. Hooke's coupling is also called universal coupling. I gave you good example also. Even I have shared you some video, Oldham coupling and Hooke's coupling in your LMS. I hope that you might have been gone through that. Okay, that's what Oldham couplings used to connect two parallel shafts when these two parallel shafts are little offsetted with respect to their axis. And Hooke's coupling can be used to where the two shafts are intersecting. We are using Hooke's coupling. Hooke's coupling is also called universal coupling. Example. And collinear axis, rigid coupling and flexible coupling. I mean, what is the rigid coupling and flexible coupling? We will see those things in the those things we are going to discuss. Now we talk about couplings and rigid coupling and flexible. What is the rigid coupling and flexible coupling? See, when the flexible coupling can be used, the small amount of misalignment, flexible coupling. I mean, the axis of the shaft, which axis of the input shaft and output shaft going to have a small misalignment, that time we can use flexible coupling. Okay, flexible coupling. Now, rigid coupling, where for example, this is a rigid coupling. Muff coupling is a rigid coupling. Here, this is input shaft. This is output shaft. The two shaft must be in collinear and should not be a misalignment. Then we are using that type of places. We are using coupling. That coupling is a rigid coupling. But flexible coupling, wherever misalignment, slight misalignment between the input shaft and output shaft, that place either in angular direction or in axial displacement or angular displacement, slight misalignment during that places we are using flexible coupling. Wherever misalignment should not be there, that places we are using rigid coupling. So now we are going to give more attention in rigid coupling and flexible coupling design. First we are going to discuss the rigid coupling. Then later we are going to discuss the flexible coupling. In rigid coupling, there are two types. I mean, this is a muff coupling under rigid coupling. I mean, split muff coupling is also under rigid coupling. Okay, now I tell you this some more points. I mean, for flexible coupling, you might have been understood that what is flexible coupling, what is rigid coupling. Okay, now in flexible coupling, as I told you that, I mean, there is the misalignment allowable. That wherever misalignment is there, wherever angular misalignment or axial misalignment displacements are there, those places we are using flexible coupling. But now, today we are not going to discuss in detailed version of flexible coupling. Just I tell you that in the introduction part, you just understand the flexible coupling due to provision of flexible elements, like we are going to use different types of elements. I tell you, I come to here. Yeah. flange coupling. Where is the flexible coupling? Yeah, yeah. See here, just for brief explanation, flexible coupling. Here, now, this type of coupling. Now, this is the unprotected flange coupling. Now, flexible coupling. Yes. See here, in this flexible coupling, we are, due to the provision of flexible elements, like we are using bush here, rubber bush, okay, and protective rubber bush and brass lining, okay, rubber bush and brass lining. I mean, this kind of components we are using to, I mean, to align whenever the two shafts are misalignment, during that time it will be automatically misaligned in this coupling. Then what is the range of alignment? I mean, for 0.5 degree angular alignment allowed using this type of coupling, and axial displacement maximum 5 mm. I mean, some books they have given mass 7 mm like that. Anyway, 5 to 7 mm axial displacement are allowed in this coupling. So hence this type of coupling is called flexible coupling. We are going to discuss later what is this, how to design rubber bush, what is the fin dimensions, and brass lining. I mean, based on application, the brass lining also, the design data book, they have given the input data. Based on that, we are going to study later. So this type of coupling is flexible coupling. Okay. Now, what is the advantages of flexible coupling? I mean, this type of coupling can be easily absorbed the shock and vibration. But rigid coupling, it cannot be absorbed any shock and vibrations. Okay. Now, that is the rigid coupling and flexible coupling advantages and the basic principle of these couplings. Okay. But rigid coupling is, I mean, rigid coupling, you can say, is based on the construction. You can say that rigid coupling is simple and inexpensive, but flexible coupling is a little complicated, complex design, and more cost. Those things you can, while looking design and while looking application, you're able to understand and you're able to say these points your own. Okay. And I mean, rigid coupling is always, I mean, wherever vibration and shock and vibration, those places we can't use rigid coupling. Okay, we can't use rigid coupling. And this is the some of the, I mean, points we should follow while designing the coupling. What are the points? The coupling should be capable transmitting the torque. Okay, first we complete this. What are the points we should follow? I come to that later. This is the sleeve muff coupling. This is the split muff coupling. We will discuss, we are going to discuss today in detailed version about this muff coupling and the split muff coupling, those things. Now this is a flange coupling. This is one flange, this is another flange. This is a shaft going to be connected here. This is the input shaft. This is the output shaft this side. This output shaft. Now this is a flange coupling. Now flange coupling. Protected flange coupling, unprotected flange coupling. Now see here, this is a unprotected flange coupling. This is unprotected flange coupling. I mean, early we discussed, this is called sleeve. Sleeve, right? This is also called sleeve. Now these are called sleeve. But here, I mean, see this one. Now we are discussing flange coupling. Here, this is the flanges. This is the flange 1. This is the right hand side, left hand side flange. This is the right hand side flange. Okay. Now this is the shaft, input to shaft. This is the output to shaft. This is the key is used here. Key provision used here this side. Key provision used here this side. Key provision used this side. Key provision used this side for securely connect the two input and securely connect the input and output shaft through the flange. Okay, hence we are using keys. But here The flange are securely also, the flange securely connected with the keys. Also, the flange is securely connected with the bolt and nut. See here, this is a bolt and nut. This type of design is called unprotected flange coupling. Why we are saying unprotected flange coupling? Because the where we are using the bolt and nuts are extended outward, the outward, I mean, away from the design of the flange, away from the geometry of the flange. Hence, it may cause us some problem while power transmission. Hence, we would like to avoid such a kind of design. Hence, we are using here protecting the circumferential rim. Here, we are using the bolt and nuts are protected circumferential ring. Then this is called protected flange. I mean, only the main difference, this only. I mean, protected type flange, unprotected type flange coupling. I mean, this is the not protected, the bolt and nuts are not protected. Here we are protecting the flange itself. This the flange design itself like that. The extended portion will be covered with the help of the flange design. The extended portion of the bolt and nut, it will be covered in the flange design, in the flange geometry, within the inside the flange geometry. Hence, this is the protective type flange coupling. But these couplings are under rigid coupling. Rigid coupling. This is unprotected flange coupling. See here, these are the unprotected flange coupling. Protected flange coupling means, just I tell you, this is the just the mean here inner portion going to be cut in like this. Then this nut will be kept inside the flange. It will not be extended away from the geometry of the flange. It will be designed based. It will be designed based on the nut dimension. It will be a extra cut will be provided. Then the nut will be securely sitting inside the flange. Hence, this is a protected type flange coupling. But these are the under. I mean, these are the under. Rigid coupling, flange coupling, sleeve coupling, and clamp coupling. This is flexible coupling. This is the under flexible coupling design. This is a flexible coupling, and whatever four couplings, this sleeve coupling and clamp coupling. This sleeve coupling, and first one is muff coupling and split muff coupling. I mean, split muff coupling. This is muff coupling. This is clamp coupling or split muff coupling. Split muff coupling. Okay. Now, I mean, we will discuss later more detail about this. This is the same flange here. This is we are using muff or sleeve. This one. Here the muff here single unit, but here in split muff coupling the muff is splitted to half. See here, this is one half, this is another half, this is one half, this is another half. That's all. We are using bolt and nut. In here in this split muff coupling, we are using bolt and nut to join the two half of the muff or sleeve here. This is a muff, we can say muff or sleeve. This is off sleeve, this is off sleeve this side. This later will be joined with help of the bolt and nut. Here only we are using single sleeve, that is muff coupling. Now this is split muff coupling. Then muff coupling, split muff coupling, and protected type flange coupling, unprotected flange coupling. These are under rigid coupling. And flexible coupling, this is under flexible coupling, flexible flange coupling. We are going to discuss bush type flange, bush type coupling, bush and pin type coupling. Okay, later we'll discuss. These are under flexible coupling, flexible coupling. Now we move to the, I mean, all them coupling is also under flexible coupling or rigid coupling. Please reflect your answer. Someone please. Alden coupling, and this is universal coupling or Hooke's coupling. What type of coupling? These are under flexible coupling or rigid coupling. Yeah, please, bus, don't delay. Hello.
Sorry, sir. Can you repeat the question?
This coupling, whatever I have shown now, Alden coupling and Hooke's coupling are under rigid coupling category or flexible coupling category. Which type of?
The rigid, sir.
Are you sure? No, but just think about that. As I told you beginning, this today class beginning, I told you, no, Alden couplings, the misalignments can be there or not. Even I have shown you, I have put a video in the LMS. I don't know how many of them gone through that, but I mean, these two shafts, this is input shaft, this is output shaft. The two shafts are parallel, but the axis of these two shafts are offsetted. But I mean, whenever the power transmission, it can be easily aligned or not. With the help of the Alden coupling, please go through the video which one I have been shared in the LMS. Now, this is the flexible coupling or rigid coupling. But tell me.
Flexible.
Yeah, flexible coupling. And universal coupling. Flexible coupling. Universal coupling also flexible coupling. Just go through, I mean, just go to the road and see the lorry and bus in bottom side, the universal joint. They're using propeller shaft. In that, they're using universal joint, right? In the undulations, when the bus or lorry, when we are driving on the road, then in wherever undulation is there, right, the power transmission should be happen in safe manner and should not be the failure, should not happen failure in the propeller shaft, right? Hence, we are using appropriate joint, I mean, universal joint. Then wherever undulation is there, I mean, the power also securely transmitted. I mean, based on these undulations, the shock and vibration, it will be easily observed by this universal joint. Wherever shock and vibrations observed by this coupling, that coupling is also called flexible coupling. That's what I told you, no? Okay. And then this is the protected type, and unprotected type is nothing but projecting parts of the nut and bolts. This projecting parts of the nut and bolts, heads, bolt, head, and maybe provided any unnecessary accidents, right? So that type of things protected. I mean, here, sorry, this is the protected type flange coupling. Yeah, this also protected, but only this is flexible coupling. Now I come to today, I mean, derivations, then we go for the problem. Now, as I told you, sleeve coupling, just to go through this, you can get more points. Almost we discussed most of the points we discussed. Now I come to the design procedure for the muff coupling. Okay, muff coupling. The muff coupling, we can say that sleeve coupling. Sorry, this is also called sleeve coupling, also called box coupling, sleeve coupling or box coupling, or box coupling, box coupling. Now see here, it is a consist of a hollow cylinder, right? This is sleeve. This is nothing but a hollow cylinder, hollow shaft, right? Hollow shaft. Okay, which is fitted over the ends of the input shaft and output shaft. Now, this is our input shaft. This is our output shaft fitted securely with the help of the keys, with the help of the shunt key, with the help of the shunt key, because this looks like a hip-guarded key. Hip-guarded key also under shunt key category. The torque is transmitted. How the torque is transmitted? the torque is transmitted from input to shaft here, input to shaft to sleeve through key, through key, okay, through key, then transmitted from the sleeve to key, then transmitted from the sleeve to output to shaft through key, through key. This is the power transmission order, okay, power transmission order. Now, what is the advantages of this key? I mean, this coupling, simplest design, right? And this coupling, I mean, simplest form of the coupling. Only here we are using two parts, only sleeve and key and shaft. Three parts only we are using. Okay, and it has been no projecting parts. Here, no projecting parts in this coupling. Okay, and this is cheaper than the other type of coupling, but only we can use for rigid type. But we cannot be used in the, I mean, the disadvantages wherever shock and vibrations are there, those places we can't use this type of coupling. Now I come to the standard procedure. This is the advantages and the disadvantages I told you that. Now, what is the diameter? I mean, this coupling, mostly we are using the shaft diameter up to 70 mm diameter. 70 mm diameter. Now, this is the shaft, this is the sleeve, this is the input to shaft, this is the output to shaft. You see here, this is the power transmission, empty, they are given already. So, okay. Now, what is the steps to be followed? I mean, once we know this, I mean, we must know how much power I want to transmit, right? Then from that, I able to find out my torsional moment. P is equal to 2 pi nt. Nt is nothing but mt divided by 60 e power 6. From this relation, now we able to find out this, what is mt. Okay, right? Now this is a standard procedure, whatever we discussed. This is nothing but initially we are considering the shaft. The power is first initially the power is input power is here. The same amount of power is going to be transmitted to the output shaft. Hence, the twisting moment, torsion moment also same in both input, output shaft as well as sleeve. Hence, we would like to use this formula to find out the torsional moment. Then this is a solid shaft. Whatever we discuss, the same concept. Tau is equal to 16 mt divided by pi d cube. Okay. Now this is the first step. From this, we can define our diameter of this shaft. Now, next step, calculate the dimensions of this sleeve. Calculate the dimensions of the sleeve. See here, this is the dimensions of the sleeve. This is the data we have taken from the, design data book. D is equal to 2d plus 13 mm. 2d, this small d is nothing but the diameter of the shaft. Length of, this is the length of the sleeve. Length of the sleeve. This is this small d is the diameter of the shaft. The capital D is diameter of the sleeve. Diameter of the sleeve. Now this is the length of the sleeve, 3.5 d. Okay. Now also we have to check the torsional stresses induced in the sleeve, because we already know here torsional stress of the shaft. Now we have to check the sleeve torsional stresses within the permissible limit or not, because now we are thinking, amount of power transmission from input shaft to output shaft. We are finding the torsion moment. The same torsion moment going to be transmitted by the sleeve also. Hence, we would like to verify the sleeve. We would like to find out the torsional stress on the sleeve also. Now the sleeve is nothing but hollow shaft. Hence, tau is equal to, this is a torsion equation we are using to find the shear stress on the sleeve, torsional shear stress on the sleeve. This is a hollow shaft we already discussed. J is equal, finally, tau is equal to mt t by j into r. T is nothing but mt into r by j. J is this hollow shaft. R is d by 2. From this relation, we are able to find out torsional shear stress on the sleeve. Third step, to find out the key length. See, key length, because Mean this is a short, this is this sleeve. One key is this side, another key is this side, then the two keys. What is that key length now? I mean length of the sleeve divided by 2, right? That's what I mean here. The length of the key is each shaft is 1/2 of the length of the sleeve. Hence, L is small l is equal to capital L by 2. Okay. Now with these dimensions, now we would like to verify our keys within our key stresses, crushing stresses and shear stresses are within safe limit or not. We would like to verify that also, right? Because how much amount of torque is transmitted in the shaft, how much amount of torque is transmitted through, I mean, in the sleeve and the key, all are same. The torque transmission is same, but corresponding that torque, our key permissible shear stress is within safe limit or not. We have to verify it. So we already discussed, I mean rectangular key, flat square key, splints and Kennedy keys. We discussed 4 keys. I mean the design concept. So based on that, this equation we are using here to find out the allowable max shear and crushing stress safe limit of this stress limit. Okay. Now I come to this problem. Now see here, design a muff coupling to connect to steel shaft transmitting the power 25 kilowatt power at 360 rpm. Speed is given, power P is given. The shaft and key are made of plain carbon steel 30 C8. This is nothing but our material notation. Okay. Now SYT, I mean yield strength and yield crushing given 400 Newton per mm square. The sleeve is made of gray cast iron. The sleeve is made of gray cast iron. I mean the sleeve material, this material made of gray cast iron, 200 Newton per mm squared ultimate strength. The factor of safety for the shaft and the key are 4. Shaft and key are 4. Factor of safety for sleeve is given 6. Now we go for the problem. Okay, solve the problem. What is our aim here? To design the muff coupling. Now first, this is the power is given, speed is given. These are the things given. For sleeve, for shaft and the keys are given this, a factor of safety given, and yield strength and crushing strength given. For sleeve, ultimate strength and factor of safety given. From this given data, we are able to find out these permissible stresses. I mean, see here, sigma T is equal to, yield strength divided by FOS, 100 Newton per mm square. Okay. Similarly, crushing, 400 divided by 400 Newton per mm square. This is a permissible. This is whatever we are discussing. Shaft and key permissible stress values. Then see here the permissible shear stress value 0.5 times SYT divided by FS. This is 50 Newton per mm square. Come to the sleeve material. The sleeve material, now sleeve material is given different material. This is the gray cast iron FG200. Ultimate strength 200 Newton per mm square. Based on that, we are defining this shear stress 16.67 Newton per mm square. Now, this is the first step we completed. In the first step, we are defining the permissible stress limits, stress values for the shaft and keys, also sleeve. Now, diameter of the shaft. Now, we know this diameter of this each shaft. Power we know. From this power P is equal to 2 pi nt. From that relations, we can find out the torsion moment. Once we find out the torsion moment, we know tau is equal to 16 mt divided by dq. We already discussed. From this relation, we are able to find out the diameter of the shaft. Right? Now, dimensions of the sleeve. Now come to the third step. Now dimensions of the sleeve. We have found now diameter of the shaft. Once we know the diameter of the shaft, we can easily find the dimensions of the sleeve from the standard design data book concept. Now D, capital D is equal to small 2D plus 13 from this relation. This is the diameter of the sleeve. Diameter of the sleeve. What is the inner diameter of the sleeve? Please, someone reflect. What is the inner diameter of the sleeve? Yeah, please, boss, don't do delay. We have to discuss other.
Small d, sir.
Yes, thank you, boss. Simple question only I'm asking. Please reflect. Thank you. Thank you. Okay. I mean, length of the sleeve 3.5D. Okay. Now come to this torsional CSS. The sleeve is within safe limit or not? Because we know the diameter of the sleeve, diameter of the inner diameter of the sleeve, outer diameter of the sleeve, and the length of the sleeve. Right? Now we know that. We know that now. These are the things we know that. Now, if we know that, we have to verify it. Either the stress limit is within permissible or not. If it is not, then we have to again go for trial and error method to find out appropriate dimensions of the sleeve. We can't change the material properties. We cannot change the material properties, but we can change our design. Okay. Now we try.
Excuse me, sir.
Yes.
Sir, that small d we found as 40.73, but we round up to 45. Suppose like
Yes.
in some 35 mm or 37 mm. So we need to take it in the multiples of 5 or something. We need
Yes,
to
yes.
take
Good
according
question.
to.
Good question. I show you. Yeah, you are correct. Yeah, this I might have been told you that. Sorry. Now, I mean, see here, our diameter is 40 mm, 40.73. This is a standard defined by the, I mean, standard. This is the data from the design data. This is a table from the design data book. See here, I mean, third 44, above 40, we are considering 44, 45 mm. Okay. So now, I mean, this is the we are round figure value we are considering. Yeah, you are correct. Now 40 mm you can consider 41 or you can consider 45. What are the available data based on you consider? Here 40 is not available, but you can consider 44 also correct. 44 or 45 both are correct only. Okay. So now this is the soft diameter. Soft diameter based on the design data book, design data values from the table. You can assume to finally 40 mm diameter. You can assume 44 or 45. It's a correct only. But when we are considering above 40, that will be a safe for the design. But we can't go below 40. As per the table data, I can consider, you can consider 44 or 45. Doesn't matter. Okay. Are you clear now?
Sir, in exam, whatever diameter we find, we will take those, or we will round off also to in the multiples of whatever we have data.
Sure, sure. I will give a clarity in the question itself. This question itself. Sure. Okay. Or else we will provide the table. You can follow. I mean, if you are following 44 up to 45, it's a correct answer. Suppose if you are taking 41 also correct only, but if you follow the design data book, that will be good as a professionally you are doing a design of the coupling.
Okay, sir.
Okay.
Thank you.
Clearly we will provide you that table. Then the confusion will be cleared. Okay. Now see here, I mean, from this, I mean, we know now diameter of the inner diameter, outer diameter of the sleeve. Then finally we have found that tau is equal to here 16.67. Now this is within limit. Sorry. Here, this is our value. I did a small mistake. Sorry, guys. Now this is our value found from the sleeve dimension. Based on the sleeve dimension, we have found the torsional shear stress created in the sleeve. 3.02 Newton per mm square. This is less than the permissible value. Then our sleeve is in safe limit. Now come to the dimensions of the key. Now see here, whatever you asked some questions. The standard cross section of the flat sunk key is 45 mm. Diameter of the shaft is 14 into 9 mm. From the table, 14 into 9 mm. 14 into 9 mm we are taking. Okay. Now, 14 into 9 mm we are taking now. Now this is the length of the key as I told you earlier. Now we know the dimensions of the key 14 into 9. Now we have to verify it. Either this dimensions of the key within the permissible limit, the stresses are within the permissible limit or not. Now this is the, we know that, right? A flat key, we already discussed it. Tau is equal to 2mt divided by dBl. We know mt, we know d, we know small l, we want to find out what is a tau. We know b value because b and h is given here. Now from this we are able to find out our shear stress of the key. How much is the torsional shear stress is subjected into the key while function transmitting the power. Now this is the shear stress, actual shear stress. If this is less than the our permissible value. Okay. Similarly, you have to find out the crushing stress. Crushing stress also same formula 4mt divided by dHL, whatever we discuss in the case. Then find out the crushing stress value 81.87 Newton per mm square. That also less than the permissible value. So whatever our component designs, all components designs are within safe limit. Okay. Now I come to this. I mean clamp coupling. Please cooperate. We have to complete clamp coupling at least today. Okay. Clamp coupling. As I told you that clamp coupling is also called compression coupling or split muff coupling. This clamp coupling or split muff coupling also called compression coupling. Okay, compression coupling. Here as I told you earlier, we have seen the muff or sleeve made into two parts. That's what I told you, two parts bolted together. Two parts bolted together. Just I bring back to you. Just I show you that bolted together. See here, this is one part. This is another part. Okay, this two part. This is split muff coupling or compression coupling or clamp coupling. Okay, now I mean one of the muff is fixed. One of the muff is fixed below and the other half is fixed above the shaft. Very simple. One of the muff is fixed below this two shaft, another muff is fixed above the two shaft, above the shaft. Then the two half of the muff going to be, this is going to be coupled together with the help of the bolt and nut. The nut and bolts are not disturb the body of the shaft. I mean, while designing this, the bolt and nut, wherever we are using bolt and nut, no, see here, this bolt and nut here, the bolt is inserted from this side, inserted this side from here. During that time, should not disturb the inserted our shaft. The bolt and nut should not be disturbed our shaft. Okay, while inserting from one end to one side to another side of the muff to couple the two muff securely. During that time, the bolt should not be disturbed our shaft. Okay, now this is the now and the power transmission. I mean, this is the where we are using this coupling used for heavy duty and moderate duty applications. We are using this type of coupling. Okay, I mean and this, I mean, power transmission. How the power transmission is happening here? Here we are using two half of the muff when we are coupled along with the shaft. Then power transmission, how it is happening? Power transmission here also we are using keys. We are using keys. Now again I come back. Yeah, now here it's available. Now what is how the power is transmitted here? In the earlier case, power transmission from shaft to, I mean shaft to shaft and sleeve through key, right, through key. But in this case, power transmission from shaft, then I mean the muff is tightly connected with the help of the bolt and nut. See here Here, this is a bolt and nuts are there. The muff is initially tightly connected, tightly held the shaft with help of the bolt and nut. Hence, power transmission from shaft to muff through frictional force. Frictional force happening between this muff surface and rod surface, soft surface. Okay, then not only frictional surface of this, and also through the key. Here we are also using key also here. Hence, the power transmission from shaft to frictional from shaft, then frictional force through frictional resistance between the muff surface and soft surface, also power transmitted through the keys from input shaft to output shaft. Only here key in muff coupling. In split muff coupling or clamp coupling or compression coupling, the power transmission happening through shaft to through frictional resistance due to, because that muff is tightly held the shaft with the help of the bolt and nuts. Hence, the frictional resistance between the shaft and muff also help to transmit the power. And also here using keys. The key also help to transmit the power from shaft to muff through keys, then output shaft. Okay. Now this is, you may expect this type of questions in the objective. Okay. Now I come to this. Now some more points. It's not possible to find out some more points you can get it your book. You go through that, you are getting more points. And we are going to discuss this coupling. In this coupling, about how the bolt is a transmitted power and bolt design. Also, we are not going to discuss the detail, very in-depth manner. Somewhat the diameter of the bolt also we are going to design based on this power transmission. Okay. Now, the power transmitted, from the input to shaft to sleeve. Now I am telling, briefly I'm telling that power is transmitted from input to shaft to the sleeve, and from the sleeve to output to shaft by means of the key and frictional resistance between the sleeve and the shaft. Okay, very important. Now come to the design, the clamp coupling or compression coupling or split muff coupling. This is the diameter of the split muff coupling 2.5D. Now this is the, L is equal to 3.5D. Now this outer diameter, length of the sleeve, this is the diameter of the shaft. Now clamping bolts. We are using the clamping bolts. Right? We are using the bolt in this coupling. Hence, diameter of the bolt is 0.2D plus 10 mm. When D less than 55 mm, we are using this. When D is greater than 55 mm, we are using this 0.15D plus 15 mm. These are the things obtained from design data book. People might have gone through laboratory experiments and field applications. Then finally they came to this information. So we are directly using this. Okay, diameter of the clamping bolt. Now the diameter of the clamping bolt can be calculated from the first principle. Let us assume that even the key, assume that even with the key, the torque is transmitted only by friction between the shaft and the coupling halves, because this muff is splitted to half. One half is sitting bottom side of the shaft, another half of the muff is sitting top of the shaft. Okay. Now we are using to couple them, griply to couple them, we are using the bolt. Okay, the clamping force, that is nothing but a clamping force we are applying through the bolt and nut here, clamping force. Okay, now what is this? When you apply the clamping force here, what is the tensile force is created now? See here, when you apply when we are tightening the nut, what will happen? Each nut I would like to each and bolt and nut I am tightening, then tensile force is happening. Then that's what we are saying here. P1 is equal to pi by 4 d squared into sigma t. This is a tensile force, tensile stress. This is the bolt dimension. P1 is pi by 4 into d1 squared into sigma 1. I mean, this is a tensile. P is nothing but tensile force. D is the diameter of the d1 is the diameter of the core, diameter of the nut, core diameter of the clamping, and sigma is permissible tensile stress. Very important. Permissible tensile stress. Now it's assumed that half of the bolts clamping pressure on the input shaft and remaining on the output shaft. I mean, see what's the meaning of it here. Now I'm taking this. Now here, I mean, this side is, for example, this side is my input shaft is sitting. This side is my output shaft is sitting. Output shaft is sitting. Then in this case, I mean, total number of bolt is 4. Total number of bolt and nut pair is used here 4. Then half of the things are sitting here in the input shaft. Half of the bolt and nuts are sitting in the output shaft side. Hence, I'm considering the clamping force is equal to N is equal to P1 into N by 2. This will P into N1 by 2. What is the total clamping force? I mean, input shaft, total clamping force is nothing but input to shaft, how much clamping force is applied, and output to shaft, how much clamping force is applied. This summation is the total clamping force. Hence here, half of the clamping force in left hand side input shaft, half of the clamping force in the right hand side in the output shaft. Hence, I am considering my clamping force is equal to P1 tensile force per 1 bolt into N, total number of bolt divided by 2. But here, both side, both any one side you have to consider, no? Hence, P1 into N divided by 2. Okay, now you might have been clear. Then this is the clamping force. Now come to this. I mean, how can I find out the torsional moment? Now, what is empty here? See, let's just see here. This is the, when we are apply the clamping force, this is the force N. Now I come to here. This is just, when you apply the clamping force, this is your shaft is here. This is now N. N, right? What is the friction resistance? Friction resistance, not very difficult, very easy. I mean, F into N. This is friction coefficient. Why I'm saying friction coefficient? Suppose I'm using a different material, maybe mild steel or stainless steel. The frictional resistance is different. Then the friction coefficient is given for various material. Okay. Hence, I'm using friction resistance here, F into N. I mean, now I know this. This is my coefficient of frictional material. Okay. Now this is now this is now Fn. Now how can I find out now torsion twisting moment here? I mean, this, I mean, horizontal force into vertical distance, right? You are very well known, right? Now Fn into, sorry, Fn into, what is this distance? This is the distance, right? D by 2. This is our torsion moment, twisting moment. Now frictional torque. Now this is, I mean, Fn into D by 2. This is Fn into D by 2. This is F into ND. This is the right side and left side like that. So F into ND. Now again substitute N value here. Then again substitute here N value. We already know N value here. N value is substitute here. Sorry, this is the N value we already know. Substitute here. We are going to get MT. I mean, frictional torque MT is equal to F into D P1 into N by 2. Now come to this. Now again, what is P1 here? I mean, from this relation, we are able to find out P1. From this relation, we are able to find out P1 is equal to 2 MT divided by FD into N. Okay. Now this P1 is nothing but how much tensile force acting at each bolt. Okay. Now I think it might be clear. Now this is the, I mean, we have to follow these process steps. I mean, first we know the power, how much power we want to transmit, we should know. From this, we able to find out the tar. I mean, we able to find out the diameter of the shaft from this relation. Okay. The second step, I mean, this is from the standard data book. Okay. Now, I mean, determine the cross section of the flat key. I mean, once we know this, I mean, diameter of the shaft, we can get it. We can take the dimensions of the key from the table. Diameter of the key, dimensions of the key, we get it from the table once we know the diameter of the shaft. Okay. Now this is the length of the key. I mean, we have to verify these key stress limits either in permissible or not. Now finally we have to find the clamping force. The clamping force, and in sometimes with the clamping force we would like to verify the permissible stress or not also. Depends on problem, depends on given data, we have to verify our coupling design. Now see this problem. Yeah, it is required to design the split muff coupling to transmit 50 kilowatt power, okay, at 120 rpm. The shaft, key and clamping bolts are made of plain carbon steel. I mean, yield strength is equal to 400 newton per millimeter square. The yield strength of the compression is 150% of the yield strength of the yield strength. I mean, SYC is given 150% of the yield strength. Very important. The factor of the safety for shaft and key, factor of safety for shaft, key and bolt is 5. The number of clamping bolt here we are using 8. Small n is 8. The coefficient of friction between the halls is given 0.3. I mean, even the design analysis, see here in the design data book, they suggested that the coefficient of friction between the sleeve and halls of the shaft, mostly we are considering 0.3. 0.3. Okay. Now come to the problem. What is our aim here? Calculate the diameter of the input-output shaft. Specify the length of the length and outer diameter of the sleeve, and find out the diameter of the clamping bolt, assuming that the power transmitted by friction. Okay. Specify the bolt diameter using standard empirical relation. I mean, we are going to use this design data empirical relation we are using. Okay, they is clearly mentioned that in the problem. And now we will see one by one. I mean, power is given, speed is given, coefficient of friction is given. This is the factor of safety, and stress limits are given for shaft, keys and bolts are given. Now first find out the permissible stress values based on given data. This is now permissible stress value of tensile for bolt and nut. This is a crushing. Now 120 Newton per mm square. This is a shear stress, because see here, I mean, they are clearly mentioned the yield strength of the compression is 150 times, 150%, sorry, 150% of the yield strength. Hence, I mean 1.5 T, 1.5 into yield strength divided by 5. Then this is our crushing stress. Okay. Now this is our, I mean, 40 Newton per mm square. This is our shear stress. This kind of questions you may expect in the objective. Okay. Now this is the diameter of the shaft. We know the power P is equal to 2 pi nt. From that we able to find out this twisting moment or torsal moment. Then we can find out the, using this relation, we can find out the diameter of the shaft. Diameter of the shaft is 80 mm. The 80 mm is, I think, available in the 80 mm. 80 mm here up to including. I think you have to consider this one. Now the dimensions of the key is from the table. Dimensions of the key we have taken from the table. Okay. Dimensions of the key we have taken from the table. 22 into 14 mm. Okay. Anyway, I come to later. First, one by one. Once we find the diameter of the shot, then we have to find out the dimensions of the sleeve. I mean, this is the diameter of the sleeve. This is the length of the sleeve. Now we have to diameter of the clamping bolts. Diameter of the clamping bolt we have to find it out. No? Now what is the P1? I mean, we know MT, we know F is given, diameter of the shaft is given, N is given. Then first to find out the force, how much clamping force we are applying in the bolt. Okay. Once we know the clamping force, now go for the finding diameter of the bolt. Okay. Once we found the clamping force, these are the information we already discussed. See here. We know MT, we know F, we know diameter of the shaft, we know this number of bolts, everything we know. From this, we are finding the clamping force. Now, once we know the clamping force, what is the tensile stress in the bolt? I mean, tensile stress in the bolt we know. The permissible value already given here. Sigma T is 80 Newton per mm squared, right? Now, this is given. From this relation, we are able to find out this diameter of the bolt. Okay. Now, diameter of the clamping bolt using empirical relation. This is the from our standard calculation. Now, this is empirical relation. Where cross verification. Okay. Now, come to the dimensions of the key from the table 80 mm, 22 into 14 mm dimensions of the key. What is the length of the key? I mean, length of the key is half of the sleeve length. I mean, capital L by 2. This is length of the key. Now, check the permissible stress value. I mean, tau is equal. This is the flat key formula we already discussed. From this, we have found the 32 Newton per mm squared from these equations. Okay, this is less than our permissible value. So our actual value of sigma c is 105 Newton per mm squared. From this relation, sigma c is equal to 4 mt divided by dhl. Substitute this value, mt we know, d we know, h we know, and l we know. Then this is our actual value, 101.5 Newton per mm squared. This is our permissible value. Hence, our actual value is less than the permissible value. So, all the designed components are within safe limit. So, if you have any doubt, please go ahead.
Sir, time up, sir.
Okay, I stop here.
Yes.
No doubt, sir.
Yeah, tomorrow we are going to discuss the flange coupling. We try to complete tomorrow. Okay. Usually the first chapter taking more time because most of the concept we are discussing, we are going to discuss here. The same concept later we are going to discuss the bearings. Some of the bearings is totally different, but some of the basics will helping. This basic will helping there. Okay. I come to meet you. How many students? Oh, okay. 70. Yeah. Okay. Kalyan, please share me the attendance. 70 students are there. 70 or in between anybody left?
In between students, some students left. 3 students left.
Okay. Yeah, please. Yesterday video I shared. Have you seen that?
Yes, sir. Alumnus you shared.
Okay. Thank you, guys. Okay, please. Already I have given you some brief explanation about the flange coupling. Please go through that. This video I will share it before this evening. Okay. Then tomorrow.
Sir, can you share the presentation, sir?
Yes, sure. I will do it. Okay.
Thank you, sir.
Yeah, thank you, guys. Thank you, Amarnath.
Thank you, sir.
Thank you,
Thank you, sir.